In this problem, what we're going to be discussing is what's called the Michelson Interferometer. And I've kind of sketched one out here for you. And the whole purpose behind the Michelson Interferometer is that it measures the wavelength of light. You can actually measure the wavelength of light with this. It's absolutely amazing. And it deals with this superposition of light in that you can have either constructive or destructive interference. So here's how it works before we actually get into the problem. So you have a light source here. You'll have a monochromatic light source. Monochromatic means one wavelength. And the yellow is going to be the first path, and the white is going to be the second path. And what the light source does is it's going to be shown, and then it's going to the light will be directed towards what's called a beam splitter. And what a beam splitter does is exactly what the name says. It splits the beam. So some of the beam gets reflected, and some of the beam gets refracted. Now there'd be another optic here for a compensator because the beam going through here has to go through some extra glass as opposed to there. So there would be a compensator drawn in there. And then what happens is, let's focus on this mirror, going the up path. So some of the light is going to get reflected off the beam splitter, and it's going to hit an adjustable mirror, and then it's going to be sent back. It actually gets sent back along the exact same path, assuming this is aligned properly. But I for my lack of artistic ability, I drew it off to the side as being the white line. And so that is going to get reflected, and it's going to come back, and it'll go pass right through the beam splitter and into either the observer, which could be you, or through some sort of detector. And you do get to count as a detector. Our eye is the most complicated detector that exists. Now, some of the light gets passed through the beam splitter and is going to hit a fixed mirror and is going to then go back. And it will be reflected off the beam splitter and back into the detector. And what happens is you move, as this adjustable mirror is moved, you'll see constructive and then destructive interference. All right? So let me go through this once more time. So you have the light source. Some of the light gets reflected up to the adjustable mirror, and some of the light gets back, is going to get refracted through the beam splitter to a fixed mirror. And then it's going to get sent back. This will get sent back. This will refract off the beam splitter when it comes back through, and this will reflect off the beam splitter. And then these two beams here, one from the adjustable mirror and one from the fixed mirror, will interfere, and they're going to interfere both constructively as well as destructive interference. So you'll see bright spots and dark spots. That's how Michelson Interferometer works. The equation for this is, it's N lambda is equal to 2 delta D, where N is equal to the number of fringes. Remember the bright spot, dark spot, bright spot, dark spot. Once again, then our lambda is going to be equal to the wavelength, and our delta D is going to be the distance between the mirrors. So you'll start this at a particular position, and then you'll move this up or back. Okay? So the question reads as such. A Michelson interferometer is illuminated on with the yellow light from a helium discharge. 500 fringes are counted as the mirror moves a distance of 0.1469 millimeters. So let's go through some of this. So N is going to be our number of fringes, and in that case, that is equal to 500. Our distance moved, delta D, is going to be equal to 0.149, my bad. It should be 69 millimeters. So this will be moved that distance. And what we want to find is we want to find lambda. And so our lambda in this case is going to be equal to twice the change in distance divided by the number of fringes. And this will be equal to 2 times 0.1469 millimeters divided by, we had 500 counts or 500 fringes that went through. When we do this arithmetic, we get 5.88 times 10 to the negative 4 millimeters, which is equal to, we can convert this into nanometers, and it's going to be equal to 588 nanometers. And so how this experiment worked was they put a light source in. This is going to be a helium discharge. The light hit the adjustable mirror as well as the fixed mirror as a result of the beam splitter. This adjustable mirror was moved 0.1469 millimeters, enough such that when they were adjusting this mirror, they were counting the fringes, bright spot, bright spot, bright spot. They were counting those fringes. They counted 500 fringes, and they had moved this mirror 0.1469 millimeters. Based on that and the calculation here, they found out that the light from the helium discharge, looking at the yellow light from the helium discharge, had a wavelength of 588 millimeters, or 588 nanometers. If you have any questions on the Michelson interferometer or any of these calculations in this chapter, please let me know.